Welcome to the section 2.6 lecture video. Today we're going to talk about the last section in chapter 2. And so what we need to talk about to finish off chapter 2 is what happens if we let the x variable go to infinity, so we let or negative infinity, so we let the x value get very, very large or very, very small, or what happens as we let x approach a number if the y values get very, very large or very, very small. So we're going to talk about limits that involve infinity. So if you take out your section 2.6 note sheets, which depending on what format of class you're in, can either be found on my math lab or under handouts or on Blackboard in the section folder, the week folder, and open to page 37. You could follow along and take notes with me. So we say that that f of x has the limit L as x approaches infinity, and write the limit as x approaches infinity of f of x equals L if for every number epsilon greater than 0 there exists a corresponding number m such that for all x in the domain of f, whenever the absolute value of f of x minus L is less than epsilon for any x value greater than m. So what we're saying here is no matter how big of a value we plug in for m, bigger and bigger and bigger, we can find some epsilon that goes with it that would allow this statement to be true, the function to get closer and closer to the limit value that we proposed. So that's the idea of a limit as x goes to positive infinity. Now, if we want to say a limit that goes to negative infinity, we can do the same basic idea. Okay, so we can say that f of x has the limit L as x approaches negative infinity written here if for every epsilon there exists a corresponding n such that the value of absolute value of f of x minus L is less than epsilon whenever we can find x less than some n, so some very large negative number. Okay. Now, in order to find these limits, one really good way to deal with this is by looking at these two examples here. So if we can get some fixed ones, then these will be very useful for finding these limits. Now, we could, so I can go and use the proof structure that we've used before for these, and I'm just going to do the plus ones. This will hold for negative ones as well. So if I want to prove that the limit as x approaches infinity of k equals k, then what I want to do is I want to use this first definition here. So I want to say the limit, so I want to say k minus its limit k is less than epsilon for any x value that is greater than m. That's what we're trying to show. Well, in this case, k minus k is 0. So 0 is less than epsilon whenever x is greater than or equal to m. So the left side of this inequality is always 0. Well, 0 is always going to be less than epsilon. So this should work for any value, right? That's what we just proved there. And then if we try to do the other one, the limit as x approaches infinity of 1 over x equals 0. We want to try and prove that. So that means we want to look at 1 over x minus 0 is less than epsilon whenever x is greater than m. And so what we want to look at for here is what do we want to use for our m value. So we want to solve this one on the left for epsilon. So this would be, for x. Okay. So now we can use the reciprocal rule to change this to x is less than 1 over epsilon. So as long as we can find a value 1 over epsilon, and epsilon doesn't equal 0, so that's fine, this will work. So remember, epsilon is greater than 0. So that means the only time this would be undefined was if epsilon was 0. Since epsilon can't be 0, this will always work. So that's the proof that this is true. Notice also here a theorem at the bottom that we're not going to prove is that all the limit laws are true when limits are plus or minus infinity. So how does that help us do these limits? Well, let's go ahead and look at an example. So what we want to do if I want to find these limits is I want to rewrite these as some version of 1 over x to a power. Okay? And the easiest way to do that is just multiply 1 over x to the highest power in the denominator. So x to the highest power in the denominator is x to the fourth. So this would be 1 over x to the fourth times 1 over x to the fourth. So if we do that, then our function becomes 9x to the fourth over x to the fourth plus x over x to the fourth over 2 over x to the fourth over x to the fourth plus 5x squared over x to the fourth minus x over x to the fourth plus 6 over x to the fourth. And now we can simplify, right? So these cancel. So that's 9 plus 1 over x to the third all over these cancel. So 2 plus 5 over x squared minus 1 over x cubed plus 6 over x to the fourth. Okay? And now remember, our limit laws tells us that in order to do this limit, so I want to take the limit of that now. So that's the limit of as x goes to infinity. I'm just going to do the goes to infinity one. They're actually going to be the same because the limits of the things inside are going to work either direction. So of h of x, so I'm just going to use some shorthand here to save me some space. And what we know is if I want to take the limit of this big expression here, I can break it down into simpler expressions. So this would be the limit as x approaches infinity of 9 plus 1 over x squared times the limit of x approaches infinity of 1 over x. Right? So notice I split this function into two pieces, one that I know the limit of times one I don't know the limit of. That's using our product rule for limits, right? That's one of our limit laws. And I can do the same thing on the bottom. So the limit as x approaches infinity of 2 plus 5 over x times the limit as x approaches infinity of 1 over x plus, minus the limit, break this one apart, so break out the 1 over x, so 1 over x squared times the limit as x approaches infinity of 1 over x plus 6 over x cubed times the limit as x approaches infinity of 1 over x. Okay? So that's a really complicated thing to write out, and I'm not going to ask you to write this out all the time. I just want to write it out the first time so we can see what happens here. If we go back to the previous page, we can see that the limit of a constant as x goes to infinity is the constant, and the limit of 1 over x as we go to infinity is 0. So what happens here is the limit as x approaches infinity of 9 is 9, but the limit of x approaches infinity of 1 over x is 0. Well, if this part is 0, 0 times anything is 0, so this just becomes 9 plus 0. And then on the bottom, a similar thing happens. I get 2. Right, the limit as x approaches infinity of 2 is 2. But all of these other ones, the limit have a limit as x approaches infinity of 1 over x, which is 0. So this would be plus 0, plus 0, plus 0. And so this ends up being 9 halves. So that's why this works. But the shorthand of how this works is if you do this division idea, the multiplying by 1 over x to the fourth divided by 1 over x to the fourth, then any term that ends up with a 1 over x, and x still in the denominator will have a limit of 0, and any constant will have a limit of that constant, whatever it is. Okay, and so that's the idea of how this works. So we can shorthand this in the second one if I do the same thing I just did above, but let's make it a little easier. So I'm going to multiply once again by 1 over x to the 5th in this case, because the highest power on x in the denominator is x to the 5th. So this becomes h of x. Here, actually, I'm going to write it over here. So that means we get 5x to the 8th over x to the 5th minus 2x to the 3rd over x to the 5th plus p over x to the 5th. And notice here, I think that p is a typo, but it doesn't really matter as long as it's really just a constant. So plus p over x to the 5th. And then we get 3 over x to the 5th plus x over x to the 5th minus 4 over x to the 5th over x to the 5th. And now if we simplify those, we get 5x cubed minus 2 over x squared plus p over x to the 5th all over 3 over x to the 5th plus 1 over x to the 4th minus 4. Okay, and so what we want to do now is look at that limit. So if I do the limit as x approaches infinity of h of x, well, the 5x cubed is something different. That's not any of the ones we know the limit of, but let's talk about for a second. If I take 5x cubed and I plug infinity into it, a very large number, what is infinity to the third? Well, it's infinity. And what is 5 times infinity? Well, it's just infinity, right? If you take the largest possible number there is, you're just going to keep getting bigger and bigger numbers, which we just call infinity. So basically what this will look like, it'll be 5 times infinity to the third minus the limit of 2 over x squared is 0, plus p over x to the 5th, the limit of that is 0. 3 over x to the 5th, that's limit is 0. 1 over x to the 4th has a limit of 0, and negative 4 has a limit of negative 4. So this ends up being 5 infinity cubed over negative 4. Well, 5 times infinity cubed is just infinity over negative 4. A positive number divided by a negative number is negative. So this limit would end up being negative infinity. Okay, and so that's the idea. So what I'd like you to do now is pause the video for a moment and try doing these other two and see what you get. Okay, so now that you've had a chance to try them, let's go through them together. So the largest power in the denominator is x to the third, so I'm going to multiply by 1 over x to the third over 1 over x to the third. So that'll give us 2x to the third over x to the third plus 7 over x to the third over x to the third over x to the third minus x squared over x to the third plus x over x to the third plus 7 over x to the third. And so we simplify. So that's 2 plus 7 over x to the third all over 1 minus 1 over x plus 1 over x squared plus 7 over x cubed. And so then if we take the limit as x approaches infinity of f of x, the limit of 2 is 2. The limit of 7 over x cubed is 0. The limit of 1 is 1. The limit of 1 over x is 0. The limit of 1 over x squared is 0. And the limit of 7 over x cubed is 0. So this is 2 over 1, which is just 2. And then the last one, same idea, right? I multiply by the largest power in the denominator, 1 over that. So 1 over x squared over 1 over x squared. So this is 3x over x squared plus 7 over x squared over x squared over x squared minus 2 over x squared. So that's 3 over x plus 7 over x squared over 1 minus 2 over x squared. Take the limit as x approaches infinity of f of x. Limit of 3 over x is 0. Limit of 7 over x squared is 0. The limit of 1 is 1. The limit of 2 over x squared is 0. So this is 0 over 1, which is just 0. Okay, and so that's the idea of how we can do limits that go as we go to infinity. Is we want to look at if it's we want to try and write everything as either 1 over x or a constant. If that can't be done, then we're going to leave some things as with the variable. But as x goes to infinity of a polynomial, we get something like what happened in this second one here in blue, where one of the terms goes to infinity. Okay, now that's one way to approach problems that look like this. Another way to approach problems that look like this is to simply think about, well, what happens if I plug in infinity or negative infinity into the problem? Okay, and we can try and look at what's going to happen in those cases. Okay, and try to figure out, that's another way to look at these problems. So let's go ahead and try that with this one on the top. Okay, so if I try that here, what I'm going to do is I'm just going to plug in the values. So this would be the cube root. I'm going to rewrite this using exponents. So this would be negative infinity to the 1/3 minus 5 times negative infinity plus 3 over 2 times negative infinity plus negative infinity to 2/3 minus 4. Okay, so now what you want to try and do is you want to try and simplify that. Well, a negative to an odd power is still going to be negative. So this would be negative infinity to the 1/3. Negative times a positive is positive, so that'd be positive 5 times infinity plus 3 over negative 2 times infinity. Negative infinity to the 2/3 is going to become positive infinity minus 4 to the 2/3 minus 4. Okay. Now, as we look at this one, this is when things start to get interesting, is you have to start thinking about the powers. Now, the largest power in either the top or the bottom is going to be the one that controls what happens to infinity, right? Because infinity to the second power is a much larger number than infinity to the first power. In this case, the largest exponent here is infinity, is this infinity here, right? Because this is infinity to the first power. So this is the only term that's going to matter, is the one with the highest exponent. Similar thing happens on the bottom. I've got infinity to the first power. I've got infinity to the 2/3. So this is the only term that's going to matter. Okay? Because if you take infinity to a higher power and you add or subtract an infinity to a lower power, in the long term, that doesn't matter. It's like if you take 1 trillion and you subtract $1 million from it, it doesn't really change the value by enough to matter, except we're talking about even larger numbers than 1 trillion, so it affects it even less. So those are the only two terms that are going to matter, the two with the highest exponents. So this limit will end up being just 5 times infinity over negative 2 times infinity. Notice those have the same exponent, so they cancel each other out, and this will just end up being negative 5/2. Okay? So that's another way you could think about these, is this is more of a conceptual way to look at these. So the same thing goes on down here, right? So if I tried the same idea here, this would be 4 minus 3 times negative infinity to the 3rd over the square root of negative infinity to the 6th plus 9. Okay? So if we look at the top here, first deal with this infinity in this term. So let's just deal. So this would be 4. We've got a negative times a negative to the 3rd. So that's going to end up being positive 3 times infinity to the 3rd over the square root of negative to an even power is positive. So this will be infinity to the 6th plus 9. Now in both cases, do the 4 plus and the plus 9 matter at all in these? Not really. Because if you have $1 trillion and someone hands you a $4 bill, it's not going to matter to you that much. Okay, so these would be the same as, once again, the terms that matter are the terms with the largest exponents with infinity. So this would be 3 times infinity to the 3rd over the square root of infinity to the 6th, the square root of infinity to the 6th. Well, what is the square root of something of 6th power? Well, it's to the 3rd power. So this is 3 times infinity to the third over infinity to the third. Just like in the problem above, those exponents cancel, so we just get 3 would be our limit. Okay, so this is just kind of another way to think about how these limits work. Okay, so what I'd like you to do at this point is go and pause the video for a second and try these last two. Okay, so now that you've had a chance to try these, let's go ahead and talk about these together. Okay, so same idea here. Plug in the things. In this case, they're both positive infinity. This is 2 plus the square root of infinity over 2 minus the square root of infinity. In this case, the 2 plus and the 2 minus don't matter because adding a 2 to infinity isn't going to change it enough to matter. So this will be the square root of infinity over the negative square root of infinity. Once again, those cancel, leaving me with 1 over negative 1, which is just negative 1. In the second one here, same idea. We'll plug in the infinities. So infinity squared plus 1 over infinity plus 1. So that's going to be the square root of infinity squared over infinity. So that's infinity over infinity, which is just 1. Okay, so those are two different ways to think about how these work. Okay. So that's what you do when you're dealing with limits where the x is approaching infinity or negative infinity. Now what we want to talk about is what happens if instead of having the x approach infinity or negative infinity, we approach a value and the y values go to infinity or negative infinity. So for example, if I were to look at these two limits here, let's just go ahead and look at graphs of them because that's going to be the best way to do this. So if I bring up my ClassCalc app, or you can use another graphing app if you want, and I do 1 divided by x, as I get close to 0, notice what happens. On the right-hand side over here, notice that this tail is going up forever. If we zoom way out, oops, out. Well, I'm not hitting things right, sorry. I don't know why it's doing that. Okay, there we go. Notice that this just gets bigger and bigger and bigger. As I follow along on the right-hand side, look how big the y values are getting. I'm currently at 0.013 and I'm at 77 something. That's going to keep going on forever. This will just get bigger and bigger and bigger until it gets to positive infinity. On the other side, notice how it goes down forever. So these limits, based on the graph, which here we can just sketch here real quick. Okay, so this graph looks something like this. Okay, so the limit as x approaches 0 on the right as of 1 over x is positive infinity, and the limit as x approaches 0 from the left is of 1 over x is negative infinity. And that is a fairly common thing that can happen. And that's the best way to approach problems like these, is simply to graph them and look at what their limits are based on the actions of the graph. So like, for example, if I graph the next one, so 2x divided by x plus 8, what you'll notice is over here at 8, as we get closer and closer, as the x values get closer and closer to negative 8, the y values are not being accurate, but you can see from the picture of the graph that the y values are going up and down to positive and negative infinity. Okay, so on the right side it went down, so that's negative infinity. On the left side it went up, so that's positive infinity. Okay, so that's the idea. So I just want you to look at the graphs of these. There's a bunch of typos on this problem, so I'm just going to go ahead and skip it for now. I think you've seen the examples. So why don't you go and flip to the next page, pause the video, and try doing these problems. Okay, so now that you've had a chance to try these, let's go ahead and just look at them. So same thing we just did here, graph a function using whatever graphing app you want to use. And so for this first one, as we get close to 3, we can see that on the right-hand side, it goes up forever. Right, on the right-hand side, this goes up forever. And on the left-hand side, it goes down forever. Okay, So on the right-hand side, our limit is positive infinity. On the left-hand side, it's negative infinity. Okay, and then we can do the same thing for these other ones. So we've got x. Sorry, I already forgot what it was. X divided by x squared minus 1. Okay, and so what do you notice at positive 1? Well, you notice on the right-hand side it goes up forever, and on the left-hand side it goes down forever. Over here at negative 1 on the right it goes up forever, and on the left it goes down forever. So the limit as x approaches 1 on the right is infinity. The limit as x approaches 1 on the left is negative infinity. The limit as x approaches negative 1 on the right is positive infinity. And the limit as it approaches negative 1 on the left is negative infinity. Okay? So that's the idea. And then this last one. Let's just try that. So x squared minus 1 over 2x plus 4. Okay, and so at negative 2, you'll notice that on the right-hand side it goes up, and on the left-hand side it goes down forever. So this one is positive infinity, and this one is negative infinity. But what you should notice at 1 and 0 is that at 0, we get negative 0.25, and at 1, we get 0. So those limits are not infinities. So it's still perfectly fine to get limits that are not infinity. So this was 0, and this one was negative 1/4, negative 0.25. So when you're doing these limits, just because it's division like this, don't assume that it's what's happening at these places where the graph is going to infinity. Make sure you're actually checking the given values. And this leads us to the idea of asymptotes. So if I look at this graph that we have here, this graph is a good example of a graph that has asymptotes. These two places right here, where we're going to infinity and to negative infinity, is what's called a vertical asymptote. There is a line that is not part of the graph, but that the graph is kind of bounded by, the graph is bounded by. Because on the right-hand side, we get closer and closer and closer to this vertical line, but we never quite get there. Okay, and on the left-hand side, the same thing is true. Okay, and these are going to happen when the simplified function is undefined. Okay, when the simplified function is undefined. We also can get horizontal or oblique asymptotes. Notice that as I go off to infinity over here on the right, as I let x go to infinity, it appears that this thing becomes a line, a straight line, and that's what's called an oblique asymptote, or a slant asymptote. So let's go ahead and fill in those definitions. So a line y equals b is a horizontal asymptote and that's not a typo. There really is a p in this word, asymptote, of the graph of a function y equals f of x if either the limit as x approaches f of x as x goes to infinity equals b, or the limit as x goes to negative infinity of f of x equals b. If the degree of the numerator of a rational function is 1 greater than the degree of the denominator, the graph has oblique or slant asymptote. We find an equation for the asymptote by dividing the numerator by the denominator to express f as a linear function plus a remainder that goes to 0 as x approaches infinity. So we'll look at an example of what that means here in a second. And a line x equals a is a vertical asymptote of the graph of a function y equals f of x if either of the following two things happen. Okay. So the way we find horizontal or oblique asymptotes is seeing what happens to the limit as we let x go to infinity. Okay, so let's look at that for each one of these. Okay, so in the first one, if we find the limit as we let x go to infinity of negative 3 over x minus 3, okay, so we could use the division idea. So divide each term by x. So this would be negative 3 over x minus 3 over x. So that's the limit as x approaches infinity of negative 3 over x over 1 minus 3 over x, which is 0, negative 0 over 1 minus 0. So that would just be 0. So we have a horizontal asymptote at y equals 0 because the limit as x equals infinity was b. In this case, b was 0. So this has a horizontal asymptote at b. If your graph has a horizontal asymptote, it will not have an oblique asymptote. Okay, so that's our horizontal asymptote. So let's try that for the other ones. So the limit as x goes to infinity of 2x over x plus 1. So that's the limit as x goes to infinity. Divide everything by the highest power in the denominator, which is x. So this would be 2x over x over x plus 1. So that's 2 over x over 1 plus 1 over x. The limit of 2 is 2, the limit of 1 is 1, and the limit of 1 over x is 0. So this would be 2 over 1, which is 2. So y equals 2 is our horizontal asymptote. Sorry, I forgot to write the limit here. Okay. And then with the last one, if I try to do the same thing, divide by the highest power in the denominator, so that's going to be the limit as x goes to infinity of x squared over x minus 1 over x over 2x over x plus 4. So that's the limit as x goes to infinity of x minus 1 over x over 2 plus 4. So that's going to be infinity minus 0 over 2, plus 4 over x. Plus 0, so that's going to be infinity. So there we got a limit that's infinity, so we're not going to have a horizontal asymptote. Instead, we're going to have an oblique one. So to find that oblique asymptote, what we have to do is we have to do polynomial division. Okay, so we have to take x squared plus 1 divided by 2x plus 4. Okay, and you may or may not remember how to do that, but the way you do polynomial division is you ask yourself, what do you have to multiply 2x by to get x squared? And the answer to that is 1/2 x, right? Because 1/2 times 2 is 1, x times x is x squared. And then we do the multiplication, so that would be x squared plus 2x, and then we subtract. So x squared minus x squared cancels. 0 minus 2x or 1 minus 2x would be negative 2x plus 1. And now we do that again. So 2x goes into 2x negative 1 times. So multiply by negative 1, so we get negative 2 minus 4. Negative 2x minus negative 2x is 0. 1 minus negative 4 is 5. And so what we get is we've changed this function to be, I'm going to write it up here, y equals 1/2 x minus 1 plus 5 over 2x plus 4. And so what happens is if I let x go to infinity, this part over here goes to 0, right? Because 5 divided by a really, really, really big number is going to be close to 0. So that part's going to go away, and our asymptote is this line. So we're going to get closer and closer to that line. And that's how you find an oblique asymptote. To find a, okay, so that's the horizontal or oblique. So it's basically all about finding the limit as x approaches infinity. To find vertical asymptotes, what you want to do is you want to look for where is the denominator undefined. So in this case, it would just be x minus 3 equals 0. So that would just be x equals 3 is my vertical asymptote. The second one, x plus 1 equals 0. So x equals negative 1 is my vertical asymptote. And for the last one, 2x plus 4 equals 0. And so 2x equals negative 4. So x equals negative 2. Okay. And if you look at the graph of any of these, you can confirm what's being said. So we already have this last one graph, so just let me look at that one. If you look at this, you can see that the vertical asymptote is happening as x gets closer and closer to negative 2, right? As x gets closer to negative 2, that's where it's going to infinity or negative infinity down here. And you can see that we've got a line with a negative y-intercept, about negative 1, and a slope of about 1 over 2 for this oblique asymptote. It goes up 1 over 2, and that's what this line is getting closer and closer to. So that's the idea of asymptotes. Okay, so what I'd like you to do now is pause the video and try the 3 problems on this page, and once we're done with that, that'll be it for section 2.6. Okay, so now that you've had a chance to try these, let's run through them together. So start by finding the limit as x approaches infinity of 1 over x minus 1. So that's the limit as x approaches infinity of 1 over x over x minus 1 over x. So that's 0 over 1 minus 0, which is 0. So y equals 0 is our horizontal asymptote. And the vertical asymptote is just at x minus 1 equals 0. So that's x equals 1. Okay. Second one, same idea. Start by finding the limit. So the limit as x approaches infinity of x plus 3 over x plus 2. So that's x over x plus 3 over, sorry, let me remember to write the limit. So the limit as x approaches infinity of x over x plus 3 over x over x plus 2 over x. So that's the limit as x approaches infinity of 1 plus 3 over x over 1 plus 2 over x, which is 1 plus 0 over 1 plus 0, which is 1. So y equals 1 is our horizontal asymptote. And then we can set the denominator equal to 0 to get our vertical asymptote. So x plus 2 equals 0. So x equals negative 2. And then for the last one, the limit as x approaches infinity of x squared plus 1 over x minus 1 is x squared over x plus 1 over x x minus 1 over x. So that's the limit. Sorry, I forgot it in the last step, but I'll just add it in here. Is x plus 1 over x over 1 minus 1 over x. So that's infinity plus 0 over 1 minus 0. So that's infinity. So that means we're going to have an oblique asymptote. So now you need to take x squared plus 1 divided by x minus 1. So what do you have to multiply x by to get x squared? X. X times x is x squared. X times negative 1 is negative x. X squared minus x is 0. 1 minus x is negative x plus 1. What do you have to multiply x by to get the opposite of x? I mean, sorry, this should be plus x. 1 minus 1, 0 minus a negative x is a positive x. What do you have to multiply x by to get x? Positive 1. So this will be x minus 1. X minus x is 0. 1 minus negative 1 is 2. So we get y equals x plus 1 plus 2 over x minus 1. As x goes to infinity, this goes to 0. So that leaves us with y equals x plus 1. And the last thing, set the denominator equal to 0. So the vertical asymptote is at x equals 1. So that's it for section 2.6. Make sure you're doing all of your homework on my math lab for this week. If you have any questions, feel free to contact me and we can talk more about it.